Welcome to NovaSleep, where tonight we open the door to one of the most dangerous and fascinating frontiers ever imagined, time travel. For centuries we have asked if it is possible to step out of the present, to return to moments long vanished, or to leap into futures we cannot yet touch. Tonight, you will hear how modern physics brings this possibility closer than ever. Rockets that could push us into distant tomorrows, black holes where time slows to a crawl, and quantum mysteries where the boundary between past and future begins to blur. This is not a story about fantasy machines, but about the real universe bending its own rules. Stay with me, because by the end of this journey, you will see that time travel is not just a dream, it is a hidden law of nature, quietly waiting to be uncovered. By the way, if you like and subscribe to my video, this is the most effective way to support me. If you can tell me where in the world you are watching from and what time it is, I would love to read it in the comments. 1. Time slows down as you move faster, making near light speed travel a one-way ticket to the future. According to Einstein's special relativity, speed and time are inseparable partners. When an object approaches the speed of light, its internal clock ticks more slowly compared to one at rest. This is not just a perception trick, but a measurable physical fact proven by experiments with fast-moving particles. If you boarded a spacecraft that could travel at 99.9% of light speed and returned after 10 years of your own experience, Earth might have aged hundreds or even thousands of years depending on the journey. Time is elastic and velocity stretches it. The reason for this lies in the nature of space-time. To preserve the constant speed of light for all observers, time must bend and adjust depending on how fast you move. This bending creates the possibility of forward time travel without needing any magical devices. The closer your speed gets to the cosmic limit, the more dramatic the time difference becomes. For ordinary travel at cars or airplanes, the shift is microscopic, but at cosmic velocities it becomes destiny-altering. Speed grants you access to futures you would never otherwise see. The implications are astonishing. Imagine a civilization that develops propulsion strong enough to cruise near light speed. Generations of explorers could witness the distant future of humanity while only aging normally themselves. They would become living windows into centuries ahead, stepping into a time that no one on Earth could yet experience. The idea transforms rockets from vehicles of space exploration into vehicles of temporal exploration. What fascinates physicists is how consistent the rules are. No matter the scale, relativity has been verified with precision. Even the tiniest particles confirm the rule when accelerated in colliders. Time travel into the future is not a dream but a byproduct of physics that already exists in equations and laboratories. The only limit is the staggering energy required to approach such speeds. But the principle remains. Velocity is a time machine written into the structure of reality. 2. A traveller orbiting a black hole could see centuries pass outside while only days pass for them. Black holes warp space-time so severely that time itself slows near their horizons. An astronaut orbiting close to a black hole's edge would experience their watch ticking normally, yet when they looked outward, the rest of the universe would be racing ahead. Days or weeks might pass for the traveller, while hundreds of years or millennia unfold beyond the event horizon. The curvature of space-time acts like a lever that pulls time apart depending on where you stand. This is not a far-fetched guess, but a consequence of general relativity, confirmed by countless tests of gravity's effects on time. Gravity is not simply a force pulling on objects, but a bending of the space-time fabric itself. The stronger the gravity, the slower the local passage of time. Around a black hole, this slowing becomes extreme, bordering on complete suspension at the event horizon. For an external observer, the astronaut would appear to move slower and slower, frozen in place. The difference in experience creates profound questions. Could an explorer leave Earth, orbit a black hole for a short span, and return to discover that humanity had advanced far beyond their own time? This scenario, while technologically unimaginable today, sits comfortably within the framework of relativity. The black hole does not just trap matter and light, it traps time itself. It is both a destroyer and a potential portal into the far future. Philosophically, the situation challenges our understanding of continuity. If one can leap forward into history by circling an abyss in the cosmos, then time travel to the future is already available as a natural feature of the universe. It is not a machine built by engineers, but an opportunity hidden inside the geometry of space-time. Black holes remind us that the cosmos contains secrets not just of space but of time itself waiting to be tested by courageous travellers. 3. Atomic clocks on airplanes prove moving through space changes your pace through time. In the 1970s, scientists placed atomic clocks on commercial airliners and flew them around the world in opposite directions. When compared to identical clocks left on the ground, the airborne clocks disagreed by precisely the amount predicted by relativity. The eastbound flight aged slightly less because it moved faster relative to Earth's rotation, while the westbound flight aged differently due to its path. The experiment showed that even routine speeds can twist time when measured with sufficient accuracy. Atomic clocks are marvels of precision, able to detect differences of billionths of a second. Their reliability means that the discrepancies were not errors or noise, but genuine consequences of motion. This was the first major demonstration outside a laboratory that time is not absolute but depends on the path taken through space-time. Everyday travel had touched the realm of time travel, albeit in minuscule amounts. The same principle now operates continuously in our technology. Global positioning system satellites must correct for these relativistic effects, or navigation would drift kilometers off course. The corrections are applied automatically, turning every GPS device into a silent witness of Einstein's insights. Without relativity, even finding your location in a city would be unreliable. Humanity lives in a world where the fabric of time is constantly adjusted behind the scenes. These results are humbling. They remind us that we already live in a universe where time is malleable and measurable. You do not need a science fiction machine to see it. The devices we use daily depend on it. Though the effects are small at slow speeds, the principle proves that with greater velocity, the time gap can widen enormously. Airplanes gave us the first taste, but spacecraft could one day offer a banquet. 4. The closer you are to Earth's surface, the slower your clock ticks compared to a mountaintop. Gravity, like speed, alters the flow of time. A clock at sea level is deeper in Earth's gravitational field and therefore ticks more slowly than one at high altitude. The difference is so tiny it takes advanced optical lattice clocks to detect it. But the effect is real and measurable. This shows that time itself has a landscape shaped by the invisible pull of gravity. Imagine two twins, one living in the lowlands and one on a mountain. Though the difference may be a fraction of a second over many years, their lifetimes would technically drift apart. Gravity bends time just as it bends space, and our bodies, thoughts, and histories are all subject to these distortions. Every heartbeat and every thought is influenced by where we are within the gravitational field. This effect has profound practical uses. Networks of precision clocks can map gravitational potential across Earth with astonishing sensitivity, detecting underground magma flows, shifting groundwater or tectonic movement. By reading time, we can monitor the health of the planet in ways no other instrument can achieve. Time becomes a tool not only for philosophy but for geology and resource management. The principle leads to mind-bending possibilities. If tiny differences can accumulate between mountaintop and seashore, what about a starship parked near a neutron star or black hole? There, time differences would not be fractions of seconds but years. The laboratory truth on Earth scales to cosmic truths in the heavens. Gravity shapes destiny not just of planets but of time itself. 5. Astronauts aboard the International Space Station already experience measurable time travel into the future. Every astronaut who orbits Earth is technically a time traveller. Because of both speed and altitude, their personal clocks tick differently than ours on the ground. Over 6 months, an astronaut might return to Earth having aged milliseconds less than their family and friends. The difference is small, yet real and recorded with precision. Living in orbit is living in a future slightly offset from our own. The combination of special relativity and general relativity plays a role here. High speed tends to slow time, while higher altitude tends to speed it up due to weaker gravity. For the International Space Station, the balance favours a net slowing. Astronauts therefore leap forward by fractions of a second, a tiny but undeniable journey into the future. This illustrates that time travel is not a fantasy waiting for discovery. It is already occurring to humans in space. The magnitude is small only because our technology limits us to modest speeds and orbits. If humanity one day develops a propulsion capable of near light speed, the same principle will carry astronauts thousands or millions of years ahead into the cosmic future. The psychological impact of this is striking. An astronaut may spend only months away, but return to find their clock slightly younger. If this effect is magnified by future technology, travelers may watch centuries slip by outside their windows while they live normal lifespans. Spaceflight is not only an exploration of distance, but also an exploration of time, and every orbit is a rehearsal for journeys far stranger than we have yet attempted. 6. Light itself is a time machine, since every star we see shows us its distant past. When you look at the night sky, you're not seeing stars as they are now, but as they were when their light left them. Some of those photons have been travelling for thousands or even millions of years before reaching your eyes. The Andromeda galaxy, visible as a faint smudge, lies over 2 million light-years away, which means you see it as it was 2 million years ago. In this sense, starlight acts as a natural time machine, carrying us back into eras when humanity did not yet exist. This fact transforms our perception of the cosmos. When astronomers use telescopes to observe distant galaxies, they are effectively building instruments that can peer deeper into the past. The further away the galaxy, the further back in time we see. The Hubble Space Telescope and now the James Webb Space Telescope have allowed us to glimpse galaxies as they were only a few 100 million years after the Big Bang, essentially opening a window into cosmic prehistory. The strange part is that there is no way to see those objects as they are now. Their present reality is forever hidden from us until the light they emit in this moment travels across unimaginable distances to reach Earth. Our entire knowledge of the universe is therefore filtered through a temporal delay that stretches across billions of years. The present state of the cosmos lies beyond our ability to observe. This realization blends astronomy with philosophy. Each star in the sky is a memory, a ghostly reminder of a universe that has already changed. Some of those stars may no longer even exist, having collapsed or gone supernova long ago, yet their ancient light still travels to us. To gaze at the heavens is to gaze into a time machine written into the very structure of reality, a reminder that even seeing is a form of travelling through time. 7. Could a wormhole let us walk from the present into the past if the two mouths are shifted in time? A wormhole is a theoretical tunnel in space-time that could link two distant points. If one mouth of the wormhole experienced a time shift relative to the other, by moving it at near light speed, or placing it near a strong gravitational field, the two ends could become time displaced. Entering one mouth might allow you to exit not just in another place, but in another era. This idea has been studied seriously in theoretical physics, though it remains far beyond current technology. The mechanics arise directly from relativity. Time is not a universal clock, but depends on the conditions around it. By treating wormhole mouths as regions of space-time connected by shortcuts, physicists like Kip Thorne have shown mathematically that time differences could accumulate between the mouths. This would effectively transform the wormhole into a time portal as well as a spatial bridge. The challenges are immense. Wormholes would require exotic matter with negative energy to remain stable. Without it, they would collapse instantly under gravitational pressure. Even if stabilized, paradoxes loom. What happens if someone goes back and prevents the wormhole from being created in the first place? The mathematics may be sound, but nature might have hidden protections that stop such situations from occurring. Yet the possibility ignites the imagination. If wormholes exist, the universe may already contain natural time tunnels, hidden in distant galaxies or near extreme cosmic structures. Travelling through one could mean stepping into humanity's distant future or walking back into epochs long past. Though speculative, wormholes remain among the most direct paths to backward time travel proposed by science. 8. Why does relativity allow travel to the future but not easily to the past? Einstein's relativity has been confirmed repeatedly, and it clearly shows that forward time travel is not only possible but unavoidable at high speeds or near strong gravity. However, travelling backward into the past introduces contradictions. Relativity equations allow closed time-like curves, but they are unstable and prone to paradoxes. Moving forward is natural, but moving back is mathematically precarious. The asymmetry arises partly because of the second law of thermodynamics. Entropy increases, creating the arrow of time we experience. Future-directed travel is consistent with this arrow, but past-directed travel would require entropy to decrease. Reversing disorder on a cosmic scale appears impossible under current physics, which is why backward travel is so difficult. Philosophers and scientists debate whether backward travel is truly forbidden or simply hidden by natural protections. Hawking's chronology protection hypothesis suggests that the laws of physics prevent paradoxes by collapsing potential time loops before they form. If this is true, then backward travel is not merely difficult but fundamentally impossible, regardless of technology. This creates a peculiar situation. We can leap into the future by speed or gravity, but the past remains sealed behind a one-way wall. Time, in this sense, behaves like a cosmic arrow shot forward, with no clear way to turn it around. The distinction highlights that not all directions of time are equal, even though space-time equations sometimes suggest otherwise. 9. The twin paradox shows that two people can age differently depending on their path through space-time. The twin paradox is one of the most famous illustrations of relativity. Imagine identical twins. One stays on Earth while the other embarks on a near light-speed journey into space and back. When they reunite, the travelling twin will be younger than the one who stayed. This is not a trick of perception, but a real difference in the passage of time for each twin. The resolution lies in acceleration. Though both experience time dilation, the travelling twin undergoes acceleration when turning around to return. This breaks the symmetry, making the traveller genuinely younger. Experiments with particles have confirmed this effect repeatedly, showing that fast-moving systems age more slowly than stationary ones. The paradox forces us to abandon the idea of universal time. Each path through space-time carries its own unique clock, and no two paths are identical. The twins' experiences demonstrate that time is relative to motion and position, not absolute. This concept overturns centuries of Newtonian thinking and replaces it with a geometry where space and time are inseparably intertwined. For human imagination, the twin paradox represents a glimpse of what interstellar travel could mean. Explorers leaving Earth may return to find that centuries have passed for those they left behind. The paradox is not just an abstract exercise, but a preview of how future journeys could reshape the human experience of family, memory, and history. 10. A rotating black hole might contain hidden corridors where time loops on itself. Unlike a simple black hole which has a singularity point, a rotating black hole or Kerr black hole may contain a ring singularity. The geometry around this ring could allow closed time-like curves, essentially pathways where time circles back upon itself. In theory, an object entering such a region might re-emerge in its own past. This possibility emerges directly from Einstein's equations when applied to rotating masses. The structure of a Kerr black hole includes an ergosphere, a region where space itself is dragged along by rotation. Within this warped geometry, normal rules of causality break down. While no one has ever observed such a region directly, mathematical models suggest that time loops are possible within them. These loops are deeply unstable, but they tantalize physicists with the idea that nature might permit time travel in extreme conditions. The danger is enormous. Radiation, tidal forces, and instabilities could destroy anything approaching such regions long before time loops become accessible. Still, the theoretical existence of such corridors forces us to take the idea of time travel seriously, at least as a mathematical concept. If rotating black holes can bend space-time into loops, then the universe itself already contains potential time machines. What makes this more compelling is that rotating black holes are common in the universe. Most stars spin, and when they collapse into black holes, they carry that angular momentum with them. The cosmos may therefore be filled with hidden laboratories where time folds back upon itself, waiting for explorers or for mathematical breakthroughs to reveal their true nature. 11. What would happen if you entered a closed time-like curve where your future touches your past? A closed time-like curve is a solution that appears in certain versions of Einstein's equations, where space-time folds so drastically that a path through it loops back onto itself. Following such a curve would mean that your future position eventually intersects with your own past position. The concept implies that the distinction between before and after becomes blurred, and you could literally encounter yourself. This is not science fiction imagination, but mathematics written directly into general relativity. If a traveller were to enter such a curve, questions of identity and continuity would emerge. Would you remember both experiences at once, or would the loop reset you endlessly? Some physicists argue that self-consistency would prevent contradictions, meaning whatever you do on the loop must already be part of what happened. Others imagine that the loop fractures reality, spawning parallel histories with each traversal. Either way, it suggests that time is not a straight arrow but a flexible geometry with hidden folds. The implications are disturbing. If you could meet your past self, could you alter the very decision that brought you into the curve in the first place? Logic suggests paradoxes, but physics hints that natural laws might lock the events into harmony. This self-consistency is sometimes compared to a story where no matter what path you take, you always arrive at the same ending because the loop has already absorbed your choices. Even if the universe allows closed time-like curves, they may exist only in regions far beyond our reach, near exotic, cosmic structures or in conditions we cannot yet replicate. Their existence in mathematics forces us to confront the possibility that time is not linear, and if time can fold back on itself, then the future and the past may be far more entangled than we ever dared imagine. 12. Could exotic matter with negative energy stabilize a wormhole into a time tunnel? Wormholes, as described in relativity, tend to collapse almost instantly under their own gravity. For them to remain open long enough for travel, something extraordinary must hold the tunnel apart. That something, according to theory, is exotic matter, substances with negative energy density. Unlike ordinary matter, which attracts, negative energy repels, counteracting the collapse of the wormhole throat and keeping the passage navigable. Negative energy is not entirely fantasy. In quantum physics, phenomena like the Casimir effect show that regions of space can have lower than normal energy density. These are hints that negative energy is physically possible, though only in tiny, fleeting amounts. The challenge is whether such effects could be harnessed and scaled to sustain a wormhole, large enough for human travel. If so, the door to time travel might no longer be a metaphor but a genuine engineering question. If a wormhole's two mouths were time-shifted relative to each other, entering one and exiting the other would mean stepping into another era. This could allow travel not only across galaxies but across centuries. The physics does not prohibit it outright, but the technological demands border on unimaginable. Exotic matter would need to be produced and controlled in quantities far beyond anything humanity can currently manage. Still, the existence of exotic matter as a concept changes the debate. It shows that the barrier to time travel may not be fundamental but practical. The laws of physics may permit it, but only if we discover how to manipulate matter and energy at levels that stretch imagination. The possibility remains alive because exotic matter is not forbidden, it is simply elusive. 13. The grandfather paradox asks if preventing your own birth would erase your existence. This paradox is the classic nightmare of backward time travel. If you travelled into the past and stopped your grandparents from meeting, would you erase yourself from existence? If so, you could never have travelled back in the first place. The contradiction seems unresolvable in ordinary logic. It is this kind of puzzle that makes past-directed time travel such a difficult idea to accept in physics. Some thinkers argue that the paradox demonstrates the impossibility of changing the past. Instead, your actions would always align with history, no matter what you tried. This is the principle of self-consistency. The universe resists contradictions by ensuring that events loop back in harmony with what already happened. You may interact with the past, but only in ways that preserve it. Others propose that the paradox reveals branching timelines. By altering the past, you would create a new parallel history where you might never be born, but your original history would remain intact. In this view, paradoxes do not destroy consistency but generate alternate universes. Every attempt to alter the past would simply shift you into a different track of reality, leaving your own origin untouched. The grandfather paradox remains one of the most effective illustrations of why time travel to the past is so controversial. It pits human logic against cosmic geometry and forces us to question whether cause and effect are truly inviolable. Whether through self-consistency or branching, the paradox reminds us that backward time travel, if it exists, must come with rules that prevent logical collapse. 14. Some theories argue paradoxes never occur because the events adjust to remain self-consistent. The Novikov self-consistency principle is one of the most widely discussed resolutions to time travel paradoxes. It proposes that even if time travel to the past is possible, events must always arrange themselves so that paradoxes never arise. For instance, if you attempt to prevent your grandparents from meeting, something will always intervene to stop you from succeeding. The past cannot be altered because your attempt was already part of it. This principle has an elegant appeal. It maintains the integrity of physics while allowing time travel scenarios to exist. In some models, your journey into the past is not a violation but a fulfillment of history. You might even become the reason why events unfolded the way they did. What looks like a paradox becomes a loop of consistency. Experiments with quantum systems offer hints of this idea. Certain models suggest that when particles are allowed to interact with their own past states, the results naturally align in ways that preserve consistency. While these are theoretical, they support the notion that paradoxes may dissolve under the right mathematical framework. If self-consistency rules are universal, then time travel is not forbidden, it is simply constrained. Travelers might be able to witness the past and interact with it, but never in ways that alter its essential course. This transforms backward time travel from a chaotic risk into a highly structured phenomenon, with the universe itself acting as the ultimate editor of history. 15. Quantum mechanics raises the possibility that the past and future exist simultaneously. Unlike classical physics, where the past is gone and the future does not yet exist, quantum mechanics allows for stranger interpretations. Some formulations suggest that both past and future states of a system influence the present. The two-state vector formalism, for example, describes quantum systems as evolving not just from past to future, but also from future to past. This opens the door to the possibility that time may be a two-way street at the microscopic level. If both directions of time matter in quantum mechanics, then our perception of a flowing arrow may be incomplete. What we call the present could be the intersection of influences from what has already happened and what is yet to come. In this picture, the future is not entirely open and the past is not entirely fixed. They may both coexist with us in ways we cannot directly perceive. Experiments such as the delayed choice quantum eraser hint at these strange possibilities. They suggest that choices made in the present can affect how past events appear, at least in terms of measurement outcomes. While no one claims this is literal time travel, it suggests that time at the quantum level may not follow the strict linear order we experience daily. The idea is radical, but it promises new ways of thinking about time. If the future exists in some form alongside the past, then time travel may be less about moving through a river and more about shifting perspective within a timeless landscape. Quantum mechanics does not yet give us answers, but it offers tantalizing hints that our ordinary sense of time may be only a shadow of deeper rules. 16. If every moment already exists, is time travel simply moving your perception to a different slice? The block universe model, also called eternalism, describes time as a four-dimensional structure where past, present, and future are equally real. In this view, events are like locations on a map. They exist whether or not someone is standing there. The flow of time, then, is not an objective feature of reality, but a feature of human consciousness. Time travel in this model would mean moving awareness from one part of the block to another. This idea challenges the way we live. If every moment exists forever, then history is not gone, and the future is not waiting. It is already there. Our experience of moving from past to present to future is like reading pages in a book. The story is complete, but we turn through it one moment at a time. The block universe replaces the dynamic with the static, where all events are fixed in a grand structure. Philosophically, this raises questions about free will. If the future already exists, can we truly change it? Or are we simply acting out roles that are already embedded in the structure of space-time? For some, this is deeply unsettling, while for others it offers comfort. The idea that every moment of existence is preserved eternally, never lost. Applied to time travel, the block universe means that traveling to the past or future is not about altering them, but about visiting different locations within an already existing framework. It removes paradoxes, but also removes choice, presenting time as a landscape we traverse, rather than a process we shape. The arrow of time is tied to entropy, but could entropy ever reverse and rewind history? Entropy, the measure of disorder, is the foundation of the arrow of time. In every closed system, entropy tends to increase, which is why we remember the past but not the future. Spilled milk does not leap back into the glass, and shattered glass does not reassemble on its own. This relentless increase defines the direction of time in our universe. But what if entropy could reverse? In principle, the laws of physics at the microscopic level are time-symmetric. They do not prefer one direction over another. The arrow appears only statistically as the overwhelmingly likely direction for countless particles. If an improbable fluctuation were large enough, entropy could decrease, making time flow backward from our perspective. Cosmologists have speculated whether such reversals might occur in extreme conditions. For example, if the universe were to collapse in a big crunch, could entropy reset and time begin flowing in reverse? Such ideas remain speculative, but they force us to consider whether time's arrow is absolute or conditional. If entropy could be manipulated, even locally, then perhaps backward time travel might be possible. Rewinding history would not mean breaking the rules of physics, but exploiting rare statistical pathways. While no one knows if this is possible in practice, the link between entropy and time suggests that the key to reversing one lies in controlling the other. 18. Can information be sent to the past without a traveller physically going there? Physical time travel involves immense challenges, but what about sending information? Theories of faster-than-light particles called tachyons suggest they could carry signals backward in time. Though unproven, their existence would allow communication into the past without needing a person to make the journey. Similarly, some quantum models allow for retrocausality, where present measurements appear influenced by future conditions. The possibility of transmitting information backward in time raises fewer physical challenges than transporting matter, but it introduces paradoxes of its own. Could you warn yourself of an accident, and if you avoided it, what becomes of the warning? These contradictions mirror those of physical time travel, but in a more subtle form. Some proposals suggest that even if retrocausal effects exist, they may be self-limiting. The information could only arrive in ways that do not generate contradictions, much like the Novikov self-consistency principle. In this way, warnings from the future would be possible only if they did not alter the essential outcome. If communication with the past were possible, the implications would be profound. History could carry echoes of future voices, hidden in subtle patterns waiting to be uncovered. Even without machines or wormholes, the universe itself might already contain channels through which information leaks across time. 19. Why have we never seen clear evidence of visitors from the future if time travel is possible? This is sometimes called the time traveler paradox. If future civilizations eventually master time travel, why do we not see them among us today? One answer is that backward travel may be impossible despite forward travel being real. Another is that travelers exist but are invisible to us, hidden in ways we cannot detect. A third possibility is that travelers arrive in alternate timelines, never reaching our own. The absence of evidence forces us to question assumptions. Perhaps time travel requires energy so immense that no civilization could ever achieve it. Or perhaps physics protects causality by forbidding journeys into the past. Some argue that travelers may be present but constrained by rules preventing them from interfering. They may observe silently, like historians watching a live reenactment of history. Stephen Hawking once tested this by throwing a time traveler's party, inviting guests only after the date had passed. No one arrived, which he offered as playful evidence that backward travel is unlikely. Yet others argue this proves nothing. Perhaps the rules of time travel forbid such obvious displays. The silence of history may simply mean that travelers are careful. The question remains a profound one. The absence of future visitors may be proof of impossibility, or it may be proof of subtlety. If time travel ever exists, perhaps we will only recognize it when our own descendants reveal that they were always among us. 20. Stephen Hawking's chronology protection suggests nature forbids time loops before they form. Hawking proposed that physics contains mechanisms to protect causality. Whenever a time loop or paradox threatens to form, quantum effects may intervene to destroy it. This idea, known as the chronology protection conjecture, would mean that the universe enforces consistency at a fundamental level. Even if equations allow loops, reality prevents them from ever becoming accessible. The reasoning behind this is grounded in quantum field theory. Calculations show that near the formation of closed time-like curves, energy fluctuations grow without bound. These divergences could destabilize the region, collapsing the loop before it becomes usable. In this way, nature preserves the order of cause and effect by destroying structures that could undermine it. If chronology protection is true, then backward time travel is impossible no matter the technology. Wormholes, cosmic strings, and other exotic proposals would all fail before creating contradictions. The universe would not permit paradox to exist, maintaining coherence across history. Forward travel remains valid, but the past remains locked away forever. Hawking's conjecture has never been proven, but it reflects a powerful intuition. The laws of physics may not only describe the world, but also safeguard its logic. If so, then time travel remains a dream restrained not by imagination, but by the fabric of reality itself. The universe may allow glimpses of the future, but keep the past sealed in eternal silence. 21. Could tachyons, hypothetical faster-than-light particles, carry messages backwards in time? In theoretical physics, tachyons are particles that always travel faster than the speed of light. Unlike ordinary matter, they could never slow down below that barrier. If such particles existed, relativity predicts they would experience time differently, moving in the reverse order compared to our perspective. This raises the startling possibility that tachyons could carry information into the past, allowing signals to be sent backward through time. The mathematics is intriguing but controversial. Faster than light motion in relativity often leads to violations of causality, where effects occur before their causes. This is exactly what makes tachyons a candidate for time communication. Yet no experiment has ever detected a tachyon, and many physicists believe they may be purely mathematical artifacts that do not exist in reality. Still, the fact that equations allow them keeps the question alive. If tachyons could be harnessed, the consequences would be revolutionary. Imagine receiving warnings about disasters before they happen, or scientific data from experiments not yet performed. The future could whisper to the present through tachyon channels, but paradoxes would loom. What if the message you received stopped you from sending it in the first place? Such contradictions illustrate the danger of backward communication. The allure of tachyons is that they sit on the edge of possibility. They are not forbidden outright, but they challenge the stability of physics as we know it. If someday an experiment finds even a trace of tachyon behavior, the door to time travel would crack open, not through people stepping into machines, but through information streaming against the flow of time. 22. If you travelled near the speed of light, Earth would appear to age thousands of years in a single trip. Relativity teaches us that as your velocity increases, your experience of time slows down. If you were aboard a spacecraft travelling close to light speed, you might feel that only a few years passed for you, while thousands or even millions of years passed on Earth. This is not speculation. It follows directly from time dilation equations and has been confirmed on smaller scales with particles and precise clocks. From the traveller's perspective, nothing unusual happens. Your heartbeat, your thoughts, and your shipboard clock all feel normal. But when you return to Earth, you would discover that entire civilizations had risen and fallen, languages had evolved, and the world was unrecognizable. The journey would be a one-way leap into the deep future, making you an alien among your own descendants. This scenario is sometimes called the twin paradox, extended to cosmic scales. It shows that relativistic travel does not just move you across space, it also moves you across time in ways no other technology can. Time is not uniform, and high velocity reshapes it dramatically. Long interstellar voyages may one day be less about distance and more about travelling into epochs beyond imagination. Such a journey poses emotional as well as scientific challenges. Would you choose to leave behind everything you know, knowing you would never truly return? The physics makes the option real, but the human consequences are profound. High-speed travel is the most realistic time machine humanity could ever build, and its gift is a future that comes at the cost of the present. 23. Would travelling to the past create alternate timelines instead of changing our own? One of the most common ways to avoid paradox in time travel theories is to suggest that the past cannot be changed, only branched. In this scenario, travelling into the past would not overwrite your history, but create a new timeline that diverges from the original. You could meet your grandparents, but any changes you make would affect only the alternate branch, leaving your original timeline intact. This interpretation is consistent with many versions of the multiverse hypothesis. Quantum mechanics already suggests that multiple outcomes exist simultaneously, so why not extend this to timelines? Each choice creates a new branch, and backward travel would simply mean stepping into a different branch rather than altering the one you came from. This removes paradoxes but multiplies realities. The idea has deep implications. If true, then time travelers could explore different outcomes of history without fear of erasing their own existence. Killing your grandfather in the past would only create a universe where you were never born, but you would still exist in the one you left behind. This turns backward time travel into exploration rather than risk. Yet the model raises new mysteries. If infinite timelines exist, what governs which one you arrive in? Are some timelines inaccessible, or is every possibility realized somewhere? Time travel here becomes less about revisiting your own past and more about discovering alternate versions of reality, where history is endlessly diverse. 24. Could the multiverse be the solution to all time travel paradoxes? The multiverse is the idea that multiple universes exist, each with its own version of events. If this is true, then every paradox of time travel might be avoided. Traveling to the past would simply place you in a different universe where your actions are consistent, even if they differ from your original history. In this way, the universe preserves causality by spreading it across many branches. Quantum mechanics gives some weight to this idea. The many worlds interpretation suggests that every quantum decision leads to branching realities. A cat is both alive and dead, but in different universes. If applied to time travel, then the act of going backward would simply shift you into the universe where your actions already align with new outcomes. This removes contradictions by distributing them. The elegance of this solution is appealing. Instead of worrying about paradoxes, time travelers become explorers of parallel worlds. History is not fragile but endlessly duplicated, with each version immune to collapse. The traveller is free to alter events because those alterations occur in their own branch of reality, not the one they left behind. But the multiverse solution is also unsettling. It suggests that infinite versions of ourselves exist, living out countless variations of history. Time travel, then, does not reunite us with our own past, but exposes us to the vastness of alternate existence. It solves paradoxes, but at the cost of making reality unimaginably vast and complex. 25. Is déjà vu a glitch in perception or a faint trace of parallel timelines? Déjà vu is the eerie sensation of having already experienced something you know is happening for the first time. Neuroscience often explains it as a misfiring of memory circuits in the brain, but some thinkers have wondered whether it could be evidence of parallel timelines brushing against each other, leaving us with fleeting awareness of a different version of events. Could déjà vu be a window into the mechanics of time? The idea is speculative, but it captures imagination because it ties a common human experience to cosmic mysteries. If time is multi-layered, or if the parallel universes exist, then occasional overlaps might occur in consciousness. Déjà vu would then be more than a neurological hiccup. It would be a resonance between timelines, allowing us to sense alternate histories we are not meant to remember. Even if the phenomenon is entirely neurological, it still teaches us about perception and time. Our brains construct a narrative of the present by stitching together inputs and memory. When this process misaligns, the result feels like living the same moment twice. This shows that our sense of time is not just physical but psychological, vulnerable to error and illusion. Whether mundane or cosmic, déjà vu invites reflection on how fragile our perception of time really is. It blurs the boundary between memory and prediction, between past and present. Even if parallel timelines never exist, the feeling of déjà vu reminds us that the human mind already lives on the edge of multiple versions of reality, some remembered and some imagined. 26. What would you see if you watched Earth from 10 light-years away through a telescope? If you were stationed 10 light-years from Earth with a powerful enough telescope, you would not see the Earth of today. You would see it as it was 10 years ago, because that is how long light takes to travel the distance. This means the further away you are, the further back in history you observe. With enough distance, you could see humanity in the Stone Age or even watch the planet before life began. The idea turns astronomy into history. Every star we observe is a record of its past state, and every galaxy is a frozen snapshot from long ago. If technology advanced enough, we could, in theory, observe our own planet's past from far away, though by the time we saw it, the events would already be over. Observation becomes a form of time travel where photons are messengers from bygone eras. This also means that no one in the universe can see Earth as it truly is in this moment, except those on Earth itself. For everyone else, Earth is always in the past. This is true for every planet and star. Their present reality is hidden behind the time it takes for light to cross the void. The universe is a vast archive of history written in light. The concept has a strange consequence. In principle, if advanced civilizations exist billions of light years away, they might be watching a very young Earth, perhaps even seeing dinosaurs alive, but they could never see us as we are today until billions of years in their own future. Observation itself ensures that all views of the universe are time-shifted, turning the act of looking into a journey backward through history. 27. A photon never experiences time itself, so what does that mean for our concept of the present? According to relativity, for a particle moving at the speed of light, time does not pass. A photon, once emitted, travels through space but experiences no lapse of time in its own frame of reference. From its perspective, emission and absorption are instantaneous, even if billions of years separate those events for outside observers. This challenges our very idea of what it means to exist in time. If photons do not experience time, then the light we see from distant galaxies is, in a sense, eternally present for them. They left their source and arrived in our eyes without duration, even though cosmic epochs passed for everything else. The universe is filled with these timeless travelers carrying ancient information without aging. They are both ancient and immediate at once. This concept has profound implications. It suggests that the flow of time may not be universal, and that different entities can experience reality in fundamentally different ways. For us, time is a sequence. For a photon, there is only now. If so, then perhaps the present moment we experience is not the only way to inhabit the universe. It also raises the question of whether other phenomena could exist beyond time. If photons can exist without aging, could more complex systems access timelessness under the right conditions? The photon reminds us that time is not a universal rhythm, but a dimension shaped by the laws of motion and energy. Our present is only one form of existence among many possible. 28. Could time be an illusion, with past and future always coexisting in a block universe? Some physicists and philosophers argue that time is not a flowing entity but an illusion of perception. In the block universe model, all events, past, present and future, exist together as a fixed four-dimensional structure. The flow of time is simply the movement of consciousness through this structure, not a property of reality itself. If true, then time travel is not about moving through a river, but shifting perspective in an already complete landscape. This view eliminates paradoxes by removing the idea of change. Nothing is truly created or destroyed in time, because all events are eternally real. You cannot alter the past because it always exists, just as the future always exists. The sense of becoming is replaced by a sense of being, where every moment has equal ontological weight. Critics argue that this denies the vivid reality of experience where the future feels open and the past feels fixed. But the block universe handles this by attributing the illusion of flow to the way consciousness experiences events sequentially. Like reading a book, the story is complete, but the reader encounters one page at a time. The structure is eternal even if the experience is linear. For time travel, this model means that journeys are possible only as shifts of viewpoint. You cannot change history, but you can visit different parts of it. The universe becomes a timeless archive where each event is preserved forever. It is less dramatic than machines and wormholes, but perhaps more profound, suggesting that immortality lies not in living forever, but in existing eternally in space-time. 29. How would free will change if the future is already written and waiting? If the block universe is correct and the future already exists, then free will takes on a troubling ambiguity. Every choice you make has already been made, inscribed in the structure of space-time. Your feeling of deciding may simply be your mind catching up with what was always destined to occur. This raises the unsettling question of whether freedom is real or just an illusion crafted by perception. Some philosophers argue that free will and determinism are compatible. You are free because your choices arise from your own nature and desires, even if they were predetermined. Others disagree, claiming that if the future is fixed, then agency is meaningless. You're merely acting out a script already written in the fabric of reality. This debate deepens when time travel is considered. If you visited the future, would you witness events that cannot be changed? And if you tried to act differently upon your return, would you fail because the future you saw must occur? Free will in a block universe seems fragile, bound by the inevitability of events. Yet even within determinism, mystery remains. If our perception creates the sense of choice, then perhaps free will is defined by experience rather than objective openness. Whether or not the future is written, we live as though our choices matter. The question is whether time travel would confirm that belief or shatter it forever. 30. Does consciousness itself flow through time, or does it create the illusion of flow? The passage of time feels undeniable to human experience. We remember the past, we live in the present, and we anticipate the future. But is this flow a property of reality or a construction of consciousness? Neuroscience suggests that the brain integrates sensory information and memory to create a narrative of time, and without this integration, the sense of flow could vanish. If consciousness creates time's flow, then perhaps reality itself is static like the block universe model. The sense of movement from past to future may be a mental illusion, a way for the brain to process change. Patients with certain brain injuries have reported altered perceptions of time, sometimes experiencing the world as frozen or disjointed. These cases hint that time as we know it might be a product of cognition. This raises the fascinating question of whether time travel might be achieved not physically but mentally. If perception is what defines the flow, could altering consciousness allow experiences of different times without leaving the present? Practices such as meditation, hypnosis, or altered states already shift how we perceive time, compressing or stretching it in ways that feel real. For time travel in the strict sense, consciousness may not be enough. But if experience is what matters, then perhaps humans already practice limited forms of temporal shifting every night in dreams or during intense states. Time as flow may be less about the universe and more about the mind, suggesting that the real machine for time travel is consciousness itself. 31. Could advanced civilizations already use natural wormholes to skip across centuries? The idea that wormholes might naturally exist in the universe is not as far-fetched as it sounds. If space-time is as flexible as relativity shows, then under certain extreme conditions, wormholes could form spontaneously or remain as remnants from the early universe. An advanced civilization might discover these cosmic shortcuts and harness them, not only for interstellar travel but also for movement across time. In theory, if one mouth of a wormhole is time-shifted relative to the other, then travelling through it would mean stepping into another century or millennium. For us, wormholes are only mathematical possibilities, but for a civilization millions of years more advanced, stabilizing and controlling them might be achievable. They could use exotic matter or unknown physics to keep the passage open and direct its endpoints to chosen times. This would give them the ability to appear at any point in history, perhaps even observing Earth across its epochs without us knowing. The thought raises questions of whether unexplained phenomena in our past could have been the result of such temporal visitors. The existence of such technology would change everything we understand about history. Instead of progressing in a linear timeline, civilizations could leap into their own distant futures, skipping over eras of struggle or waiting for natural cosmic changes to occur. Imagine skipping forward to a time when stars have aligned differently, or backward to when the universe was young and hot. The power to manipulate wormholes would not just mean crossing light years, it would mean crossing centuries in a single step. What fascinates us is that relativity itself does not forbid this possibility. The mathematics works, though the practical requirements are beyond our reach. If advanced civilizations exist elsewhere, they might already view time as a resource to be navigated, much as we navigate space. In that sense, the absence of visible time travelers could mean only one thing: they are far better at hiding their tracks than we can imagine. 32. Why do black holes appear to freeze objects in time at their edge to distant observers? When matter falls toward a black hole, it appears to slow down and freeze at the event horizon when viewed from far away. This happens because the extreme warping of space-time stretches time near the horizon. To an outside observer, the falling object never quite crosses the boundary, instead becoming dimmer and redder until it vanishes. From the perspective of the object itself, however, it passes through the horizon in a finite amount of time. This strange duality shows that time is not absolute, but depends on perspective. The object falling in experiences a normal sequence of events, while the distant observer sees time stretched into infinity. Both views are correct within their own frames of reference, but they cannot be reconciled into a single universal timeline. Black holes force us to confront the relativity of time at its most extreme. This apparent freezing of time has deep implications for information. If objects appear suspended at the horizon forever, where does their information go? Do black holes preserve it in some way, or is it lost? This question forms the heart of the black hole information paradox, which remains one of the great unsolved problems of physics. Time itself seems to hold the answer, as if the horizon is not only a spatial boundary but also a temporal one. Philosophically, this effect challenges our intuition about beginnings and endings. From one perspective, the story continues, from another, it stops forever at the horizon. Time is not a single thread but a web, and the path you take determines whether you witness a fall into oblivion or a journey beyond. The black hole shows us that time is not just relative, it is fundamentally fractured, leaving us with more questions than answers. 33. What happens at the event horizon where time nearly stops? The event horizon of a black hole is the ultimate boundary of no return. It is the surface where the escape velocity equals the speed of light, meaning nothing, not even light, can escape once it crosses. At this edge, time itself slows down relative to distant observers. For those far away, the horizon represents a frozen barrier where all processes grind toward a standstill. But for an object crossing it, time continues normally until it meets the singularity inside. This paradoxical behavior makes the event horizon one of the most mysterious places in the universe. It is a region where relativity reaches its breaking point, and where our theories of gravity and quantum mechanics collide. Some theories propose that the horizon may not be a simple boundary, but a complex surface storing vast amounts of information. Others argue that it may even radiate energy, a phenomenon known as Hawking radiation, which could slowly evaporate the black hole itself. The horizon is also the place where our understanding of time falters most dramatically. To an outside observer, the fall into a black hole never completes. It is endlessly stretched. Yet for the falling traveller, crossing the horizon is an uneventful step forward. This contradiction suggests that time is not a universal experience, but a property defined by context, perspective, and the structure of space-time itself. If we could unlock the secrets of the event horizon, we might understand time in a way we never have before. It may be that the horizon is not just a physical boundary, but a doorway into deeper truths about causality, entropy, and the fabric of reality. At the edge of a black hole, time reveals its most alien and unsettling nature, where the distinction between stillness and motion dissolves. 34. Could white holes, the theoretical opposite of black holes, eject matter from the past into today? White holes are a speculative solution to Einstein's equations that represent the reverse of black holes. Instead of swallowing matter and trapping it, white holes expel matter and energy, refusing to let anything enter. In theory, if black holes exist, their time-reversed counterparts might also exist as white holes. Some scientists have even suggested that the Big Bang itself could have been the ultimate white hole, spewing energy and matter into a new universe. If white holes exist, they could serve as natural time machines. Matter ejected from a white hole might come from another era, or even another universe. They would not only defy gravity, but also defy our understanding of causality, throwing events forward in ways we cannot yet predict. Unlike black holes, which lead to hidden singularities, white holes would spill their secrets into the cosmos, revealing traces of what lies beyond. The difficulty is that no observational evidence has ever confirmed their existence. Black holes are abundant, but white holes may be unstable or impossible in practice. Still, they remain a tantalizing possibility in theoretical physics, because equations do not exclude them outright. If they do exist, they could provide a bridge across time, ejecting matter from a long-lost past into our present. The concept of white holes reshapes our imagination of the universe. Instead of being dominated only by regions that trap information, there may be regions that release it. The idea suggests a cosmos where time flows in multiple directions, with black holes pulling into the future and white holes pushing from the past. If ever discovered, they would prove that time's arrow is far more complex than we thought. 35. Does time emerge from quantum entanglement rather than existing on its own? One of the boldest ideas in modern physics is that time might not be fundamental at all. Instead, it could emerge from the entanglement of quantum particles. In this view, time is not a separate dimension flowing independently, but a property that arises when particles become correlated. Without entanglement, time as we know it may not even exist. This concept is inspired by experiments showing that entanglement governs not only space, but also causality. When two particles are entangled, measuring one instantly affects the other, regardless of distance. Some researchers argue that the direction of time itself could arise from this interconnection. The arrow of time may be nothing more than the growth of entanglement spreading through the universe. If time is emergent, it means that our deepest assumptions about reality are incomplete. Time would not be a stage on which events unfold, but a shadow cast by deeper processes. This suggests that time travel might not be about bending a pre-existing dimension, but about manipulating the underlying quantum fabric that gives rise to time in the first place. The implications are staggering. If entanglement truly generates time, then advanced technologies could in principle reshape the flow of time by controlling quantum states. Time travel might not involve giant machines or cosmic structures, but delicate manipulations at the smallest scales. The idea shifts the search for time travel from cosmic engineering to quantum mechanics, where the mysteries may already be within reach. By the way, if you like and subscribe to my video, this is the most effective way to support me. 36. Can future experiments prove that entangled particles influence each other backwards in time? Quantum entanglement already defies our classical intuition. Measuring one particle appears to instantaneously affect its partner, even when separated by great distances. But some interpretations suggest that this influence might not only be instantaneous, but also retrocausal, reaching back into the past. Experiments designed to test delayed choice or retroactive effects are beginning to probe whether the future can shape the past at the quantum level. If retrocausality exists, it would mean that outcomes today are influenced by measurements made tomorrow. This would completely reshape our understanding of cause and effect. It suggests that time may not be a one-way street, but a two-way dialogue between past and future. Such experiments remain controversial, but their results continue to push the boundaries of what we think time allows. Critics argue that these effects can be explained without invoking backward influence, using standard interpretations of quantum mechanics. But the fact that retrocausality remains a viable interpretation shows how fragile our understanding of time really is. The possibility cannot be dismissed until experiments definitively rule it out. If entanglement allows retrocausal effects, then time travel might already be happening at the quantum level. While no person could yet step into the past, particles might already carry influences across temporal boundaries. The challenge is whether we can ever harness such effects on macroscopic scales. 37. If the universe expands forever, does time also stretch without end? The universe is currently expanding at an accelerating rate, driven by a mysterious force called dark energy. If this continues indefinitely, galaxies will drift farther and farther apart until they vanish beyond cosmic horizons. Time itself may continue to stretch endlessly with no final boundary. The future in such a universe would be infinite, a vast desert of expansion without limit. In this scenario, time travel to the future would mean travelling into a cosmos where stars have burned out and galaxies have grown cold. The far future would be a lonely place, where matter is thinly scattered and energy grows sparse. Travelling forward would not only reveal future civilizations, but also the ultimate fate of existence itself. This raises profound questions about whether time has an end. If expansion continues forever, then the arrow of time stretches infinitely into the future. But if dark energy changes, time might collapse back, or even cycle. The uncertainty leaves us with no final answer about whether time is endless or finite. If the future is infinite, then time travel takes on a new weight. Any journey forward could carry you into a reality unimaginably distant from our own. The idea that time never ends makes the universe itself an infinite time machine, one where every possible era unfolds somewhere in the endless march of entropy and expansion. 38. Could the universe eventually collapse under reverse time's arrow? Not all cosmological models agree on endless expansion. Some suggest that the universe might one day halt its growth and begin to contract. In this big crunch scenario, galaxies would draw closer, stars would collide, and temperatures would rise until everything collapsed back into a singularity. In such a universe, the arrow of time tied to entropy might also reverse, causing time to flow backward during contraction. If this were true, then the distant future might mirror the past. Events could unfold in reverse, galaxies unforming, stars rewinding, and matter collapsing into unity. For observers, it could mean that the direction of time itself flips, leaving our perception bewildered. Such an outcome would challenge every assumption about causality and memory. The physics behind this possibility lies in entropy. If entropy decreases during contraction, then the arrow of time reverses. This is speculative, but it demonstrates that time may not be a universal constant. Instead, it may depend on the large-scale dynamics of the cosmos, shifting with its expansion and contraction. The idea offers a strange form of time travel. If the universe cycles endlessly between expansion and contraction, then the future may lead us back into the past, creating an eternal loop. Time would not be linear but circular, repeating forever in a cycle that both erases and preserves history. 39. Do time crystals, repeating structures in time, hint at deeper rules of temporal flow? Time crystals are a recently discovered phase of matter that repeat their structure not in space like ordinary crystals, but in time. They tick at intervals even without consuming energy, creating a stable rhythm in the fabric of reality. This strange property has led some scientists to speculate whether time crystals could reveal hidden aspects of how time itself is structured. The significance of time crystals is that they break time translation symmetry, one of the fundamental symmetries of physics. By doing so, they suggest that time may not be uniform, but subject to new rules at microscopic levels. They are a demonstration that time can be organized and manipulated, much like space can be crystallized. This discovery has implications for quantum computing and energy systems, but it also touches on the philosophy of time. If time can form repeating patterns, then perhaps it is not continuous but segmented, like frames of a film. Manipulating those frames might open pathways to new forms of time control, including speculative ideas about travel. Though still in early study, time crystals hint that time may be far more malleable than we thought. If repetition and order can be locked into time itself, perhaps future technologies could harness such structures to navigate across moments the way we navigate across space. Time travel may begin not with stars and black holes, but with crystals ticking in the silence of a lab. 40. Is memory itself a kind of time travel inside the brain? Every time you recall an event, your mind brings the past into the present. You are not physically there, but in your memory you relive the sights, sounds, and feelings of that moment. This is a form of mental time travel, where the brain reconstructs history and lets you experience it again. Neuroscientists argue that this ability is one of the most complex and defining traits of human consciousness. Memory is not a perfect recording, but a reconstruction. Each time you revisit the past, you reshape it slightly, blending old details with new context. In this sense, remembering is not only traveling backward in time, but also rewriting it, at least in your perception. Your personal timeline is constantly being re-experienced and redefined. This capacity extends to the future as well. When you imagine possibilities, you are mentally projecting yourself into moments that have not yet happened. The same neural systems that recall the past are used to construct the future. The brain is therefore a bidirectional time traveler, visiting both directions in ways no machine can replicate. While physical time travel remains speculative, mental time travel is a daily reality. It shows that the essence of time travel may not only be about physics, but also about consciousness. The brain already bends time, revisiting what has been and anticipating what will be, creating a narrative that defines identity and meaning. 41. What if closed time-like curves exist only in unreachable cosmic regions? Closed time-like curves are mathematical structures in relativity where paths through space-time bend back on themselves, allowing a traveller to return to their own past. They sound like pure science fiction, but equations for rotating universes, wormholes, and other exotic geometries all suggest such loops are possible under certain conditions. The troubling part is that they create paradoxes when brought into everyday contexts. One way to resolve this is to imagine that closed time-like curves exist, but only in regions of the cosmos forever beyond our reach. Such regions could be hidden near singularities, deep inside rotating black holes, or in corners of space-time warped by cosmic strings. These would be environments so extreme that no spacecraft, no matter how advanced, could survive them. The curves would exist in theory, but for practical purposes, they would remain locked away, protecting the rest of the universe from their paradoxical consequences. Time loops would be real but untouchable. This interpretation aligns with Stephen Hawking's chronology protection idea. Instead of outright banning time loops, the universe may permit them, but keep them out of our causal reach. In this way, the laws of physics maintain consistency without rewriting the mathematics of relativity. Closed time-like curves would be like fossils buried deep in cosmic strata, evidence of strange possibilities, but inaccessible to living explorers. If this is true, then time travel remains a mathematical truth, but a physical impossibility. It exists in the realm of equations and unreachable corners of reality, tantalizing but forbidden. It means the universe might contain exotic time geometries as curiosities, while keeping the main stage of existence stable and free of contradiction. 42. the arrow of time may start as a low entropy miracle. The arrow of time is defined by entropy, which almost always increases. But why did the universe begin in such an extraordinarily low entropy state that allowed time's arrow to exist in the first place? This is one of the deepest mysteries of cosmology. Without that improbable beginning, we would not experience time as a one-way journey from past to future. Instead, the universe might look timeless or chaotic, with no preferred direction. One possibility is that the Big Bang itself encoded this low entropy condition, setting the stage for everything that followed. Another idea is that our universe is part of a larger multiverse, and we just happen to exist in a rare region where entropy began low enough to produce an arrow of time. Either way, the fact that entropy was so ordered at the start remains unexplained. A cosmic miracle at the heart of time. If the arrow of time depends on initial conditions, then time travel may ultimately be tied to those conditions as well. We can move forward in time easily because entropy increases, but moving backward would require reversing entropy, a task that seems impossible under normal physics. Our inability to travel back may be written into the very birth of the cosmos. The mystery of low entropy beginnings suggests that time travel is not just a question of relativity or mechanics, but of cosmology. To unlock time, we may need to understand why the universe started in such a strange state. Without that knowledge, the arrow remains unexplained, and the doorway to the past remains sealed. 43. Poincaré recurrence implies that histories can nearly repeat. In a closed system with finite energy, the laws of probability suggest that given enough time, the system will eventually return to a state very close to one it has been in before. This is called Poincaré recurrence, and while the timescales involved are unimaginably vast, it means that the universe might one day resemble its past with extraordinary closeness. This idea transforms time from a linear story into a repeating cycle on the largest scales. Civilizations, stars, and galaxies could all emerge again in forms nearly identical to what came before, separated by stretches of eons. To us, this would be indistinguishable from true time travel, because the recurrence would recreate familiar configurations. History would not be preserved, but regenerated by chance. The problem is that recurrence times are so long they dwarf the age of the universe as we know it. It could take trillions upon trillions of years for any meaningful repetition to occur. Still, the mathematics suggests that recurrence is inevitable in a closed system. If our universe is finite and isolated, then it will eventually replay its story, even if none of us are here to see it. The idea blurs the line between determinism and randomness. It means that time travel may not be about moving backward, but about waiting long enough for the universe to recreate the past. While impractical, it reminds us that time is not only directional, but cyclical in subtle and hidden ways. 44. The Loschmidt reversal challenge haunts the second law. The second law of thermodynamics says that entropy always increases, defining the arrow of time. Yet the fundamental laws of physics are time-symmetric. They work the same forward or backward. Joseph Loschmidt challenged this by asking, if the laws allow reversibility, why does entropy move only forward? This paradox still puzzles scientists today. The challenge highlights a gap in our understanding of time. If every motion of particles can be reversed, then the second law must come from initial conditions or probability rather than necessity. Entropy increases because it is more likely, not because it is inevitable. This subtle distinction has profound consequences for time travel. It means that the arrow of time may not be absolute but conditional. If conditions could be arranged just right, perhaps entropy could decrease locally, allowing a reversal of time's arrow. This is speculative, but it suggests that the key to time travel may not be engineering a machine, but engineering improbability. To reverse time would mean to create a system where entropy moves backward instead of forward. The Loschmidt paradox reminds us that the arrow of time is not as ironclad as it seems. It is a statistical rule, not a law carved in stone. If we can understand why entropy always seems to win, we may uncover pathways to moments where time itself can be bent or even reversed. 45. Boltzmann brains are minds that arrive from rare fluctuations. In an infinite universe with enough time, random fluctuations could assemble self-aware observers, known as Boltzmann brains. These hypothetical beings would appear fully formed, complete with false memories, only to dissolve back into chaos moments later. They are an unsettling consequence of applying probability to entropy on cosmic scales. The existence of Boltzmann brains raises disturbing questions about time. If such fluctuations are more likely than entire universes forming, then what does that mean about our perception of reality? Could our sense of the past be nothing more than a temporary illusion inside a fluctuation? If so, time travel would not mean moving through a real history, but escaping from a temporary hallucination of order. While most physicists believe that our structured universe is far more stable than Boltzmann brains, the concept forces us to consider time as a statistical phenomenon rather than an absolute. It suggests that memory, history, and continuity may be fragile and conditional, depending on improbable order that could dissolve at any moment. For time travel, this implies that our certainty in the past is less solid than we think. If minds can spontaneously appear with memories of histories that never occurred, then perhaps the past itself is not as fixed as we believe. Boltzmann brains are unlikely, but they remind us that time and consciousness are tied together in ways that defy easy answers. 46. Holography says a volume of reality is coded on a surface. The holographic principle suggests that everything within a volume of space can be described by information stored on its boundary. In this view, the three-dimensional world we experience might be a projection from a two-dimensional surface. If so, then time itself could also be encoded in this holographic structure, making our perception of flow a translation of surface data. This radical idea emerges from black hole physics. Calculations show that the information content of a black hole scales with the area of its horizon, not its volume. Extending this logic suggests that all of space-time may be a hologram, with our sense of motion through time arising from the unfolding of encoded information. If time is a holographic property, then time travel may involve accessing the code directly, rather than moving through physical reality. By rewriting the surface information, one could in theory alter the projection, revisiting past frames or advancing into future ones. Time becomes a playback function rather than a flowing river. Though still speculative, holography has gained traction in physics because it unites gravity and quantum mechanics in surprising ways. If confirmed, it would mean that time itself is not fundamental, but an emergent property of information storage. The possibility of editing that information could be the true key to time travel. 47. Complexity growth in quantum systems acts like a clock. In quantum mechanics, the complexity of a system's state tends to increase as time passes. This growth is so reliable that some physicists suggest complexity itself could serve as a kind of internal clock for the universe. Instead of entropy alone defining time, complexity may be an equally fundamental measure of its flow. If complexity is a clock, then time travel might involve rewinding or fast-forwarding complexity growth. This could mean undoing the quantum operations that built the present state or accelerating them to leap forward into possible futures. Complexity provides a mathematical framework for imagining how time could be manipulated at the quantum level. The connection is especially intriguing in black hole physics, where the growth of complexity inside a black hole appears linked to the growth of its interior volume. Some researchers believe this points to a deep connection between time, complexity, and geometry. If true, then complexity may not just measure time, but generate it. If we ever learn to control complexity in quantum systems, we may discover that we are not just building computers, but building time machines at microscopic scales. Time might be nothing more than the measure of computational depth, and changing that depth could unlock entirely new experiences of reality. 48. Black hole interiors may be built from quantum circuit depth. Some theorists argue that the interior of a black hole grows not in a physical sense, but in terms of quantum complexity. The deeper the complexity of its quantum state, the larger its interior volume becomes. This suggests that time inside a black hole is directly tied to the growth of quantum information rather than ordinary clocks. If this idea is correct, then entering a black hole might mean stepping into a region where time is defined differently than outside. The ticking of clocks and the flow of seconds could be replaced by the growth of circuit depth. This means that black hole interiors are not just places of extreme gravity, but also laboratories of quantum time. The relationship between geometry and computation here is profound. It suggests that the fabric of reality may itself be a kind of quantum computer, with time emerging from the way information is processed. Traveling into such a region would not just be dangerous, It would be a journey into a fundamentally different kind of time. The lesson is that time travel may not always look like a moving arrow. In black holes, time can be constructed from quantum operations, meaning that our familiar flow is just one of many possibilities. If complexity builds volume, then perhaps we can learn to navigate time by understanding the rules of information rather than the pull of gravity. 49. The firewall puzzle tests the smoothness of horizons. The black hole information paradox led to the proposal of a firewall at the event horizon. Instead of being a smooth passage, the horizon might burn any matter that attempts to cross it, destroying information in the process. This shocking idea contradicts general relativity, which says that crossing the horizon should be uneventful, but it may resolve contradictions with quantum theory. If firewalls exist, they fundamentally alter our view of time near horizons. Instead of a seamless flow into the future, the horizon becomes a violent barrier where history ends abruptly. Information would not survive to reach the singularity, and time for the falling observer would terminate in fire. This would make the horizon the most extreme endpoint of time imaginable. The puzzle is that different theories make conflicting predictions, and experiments cannot yet decide between them. If horizons are smooth, time continues normally for the falling observer. If firewalls exist, then time is torn apart at the horizon. This conflict remains one of the most pressing problems in modern physics. For time travel, the firewall debate shows how fragile our understanding really is. Depending on which theory is correct, a black hole could be a doorway into other times or a wall where time ceases entirely. Until the paradox is resolved, we cannot know whether horizons are passages or boundaries. 50. Complementarity says no single observer sees contradictions. Black hole complementarity offers a possible resolution to the paradox of information. It suggests that what an outside observer sees and what a falling observer experiences can both be true, even if they seem contradictory. From the outside, information never crosses the horizon. From the inside, it passes smoothly through. Each perspective is consistent, but no single observer can access both stories at once. This principle protects the consistency of physics by limiting what observers can know. Time may look different depending on where you stand, but contradictions never occur because no observer experiences both at once. It means that the flow of time is not universal but observer-dependent, shaped by position and perspective. Complementarity echoes broader lessons in relativity. Time is not a shared universal stage but a local experience that depends on speed, gravity, and vantage point. By extending this principle to black holes, physicists hope to preserve both relativity and quantum theory without sacrificing consistency. For time travel, complementarity implies that contradictions may never truly exist. What seems like a paradox from one perspective may dissolve when viewed from another. If time is observer-dependent, then travelling through it might not create logical impossibilities. It may simply reveal that reality has multiple consistent views of the same events. 51. Shifting reference frames can swap what counts as past and future. One of the most unsettling results of relativity is that the order of events is not absolute. Two observers moving at different velocities can disagree about whether one event happened before another, or even whether they occurred simultaneously. What is the past in one frame can be the future in another. This is not a trick of perspective, but a fundamental feature of space-time geometry. Imagine two flashes of lightning striking different ends of a moving train. To someone standing on the ground, the flashes may look simultaneous. To someone riding the train, one flash may appear to occur first. Neither observer is wrong, their reference frames define time differently. This simple thought experiment reveals that time's ordering depends on motion, undermining the idea of a universal now. Applied to cosmic scales, this relativity of simultaneity has profound consequences for time travel. If the classification of past and future depends on the observer, then travelling close to light speed could shift entire events from one category to another. An event that seems fixed in history for one person could appear as yet to occur for another. This undermines the solidity of time and reveals how fragile our intuitions really are. The lesson is that time is not a single thread woven for everyone. It is a fabric with different orientations, twisted by velocity and position. When reference frames shift, the labels of past, present, and future bend as well. This opens the door to imagining journeys where those labels can be manipulated deliberately, creating paths that cut across what we normally think of as fixed history. 52. A photon is its own clock that never ticks at all. In relativity, every object carries its own proper time, the time measured along its path. For us, time flows steadily as our proper time ticks away, but for a photon which travels at the speed of light, proper time does not pass at all. From the photon's perspective, emission and absorption are the same moment. The billions of years between them collapse into a single instant. This makes photons unique among all things in the universe. They do not age, they do not accumulate experience, and they never move from one moment to the next. They are eternal messengers, carrying information across the cosmos without ever experiencing the journey themselves. For them there is no then and now, only the eternal now. If light can exist outside of time, what does that mean for us? It suggests that time may not be a universal feature of reality, but a property of how matter and energy interact. Photons reveal a way of being where time is irrelevant, hinting that the flow we experience is not a law of nature but a condition of our existence. This reframes time travel. Perhaps it is less about moving ourselves and more about becoming like light. The photon teaches us that timelessness is not only possible but already present in the universe. Every beam of light carries proof that duration can vanish. If physics can explain how something can live outside of time, then perhaps future breakthroughs could help us step into a similar state, moving through history not as aging beings, but as ageless messengers. 53. Neutrino superluminal claims collapsed under a loose cable. In 2011, a shocking announcement from the Opera experiment in Italy suggested that neutrinos had travelled faster than light. If true, it would have upended relativity and opened the door to backward time travel, since faster-than-light motion leads to causal reversals. For months, the physics community debated the meaning of the result, wondering whether time travel might finally have a physical foothold. The excitement ended when researchers discovered the true cause, a loose cable connection in the experimental setup. Once corrected, the neutrinos behaved as expected, always slower than light. The dream of confirmed superluminal travel collapsed, but the episode demonstrated how much is at stake in precision experiments. A tiny mistake nearly overturned one of the greatest pillars of physics. Though the claim failed, it revealed how hungry we are for cracks in relativity. If anything could travel faster than light, time travel would move from speculation to engineering. It also showed how rigorous science must be when claims touch the deepest foundations of reality. The universe may not give up its secrets easily, and errors masquerading as discoveries remind us how fragile progress can be. Even if neutrinos never broke the barrier, the episode sparked renewed interest in the question. What if one day we do discover a particle that ignores the cosmic speed limit? Could that particle be the key to messages from the future or visits to the past? The story reminds us that time travel might hinge not on wormholes or machines, but on the strange behavior of particles too small to see. At 54, quantum tunneling times invite debate about speed through barriers. Quantum tunneling is a process where particles cross barriers they should not have the energy to overcome. When measured carefully, some experiments suggest that tunneling may occur faster than light would normally allow. This has raised debates about whether tunneling is a loophole in causality, hinting at time travel on the quantum scale. The problem is that tunneling times are difficult to define. Does the particle spend time inside the barrier, or does it skip across without duration? Different interpretations give different answers. Some physicists argue that no causality is broken, while others wonder if tunneling reveals a deeper truth about how time operates at microscopic levels. If tunneling truly bypasses normal limits, then quantum systems may already perform tiny acts of time defiance. While not useful for sending people into the past, such effects might one day be exploited for faster communication or exotic technologies. They show that even on the smallest scales, time is not a rigid wall but a negotiable boundary. Whether tunneling breaks causality or not, it illustrates that our grasp of time remains incomplete. Particles seem to blur across barriers in ways that defy our intuition of steady progression. If particles can take shortcuts through time, perhaps larger systems could one day be coaxed into doing the same. 5. Attosecond metrology watches electrons with near time freeze. Attosecond physics has given humanity the ability to measure events on timescales of billionths of a billionth of a second. At these intervals, we can watch electrons move inside atoms, capturing dynamics that were once unimaginable. The instruments create pulses of light so short that they act like strobe flashes, freezing time on quantum scales. These experiments show that time is not just an abstract flow, but something that can be sliced, segmented, and probed. The ability to watch electrons in near real time reveals how the fundamental machinery of the universe operates. It is as if we have learned to slow down nature's film to watch each frame of reality. This level of control transforms time into a laboratory variable. Instead of being passive observers of its flow, we can now interrogate it, pushing precision into realms that were science fiction only decades ago. Attosecond metrology hints that time may one day be as manipulable as space, opening doors to new technologies and perhaps even time control. The promise here is not to assess time travel yet, but time mastery. By controlling time on microscopic scales, we may learn principles that could eventually apply to larger systems. Attosecond research is a reminder that time is not untouchable. It is already being measured, frozen, and manipulated in the lab. 56. Optical lattice clocks compare time across a human hair of height. The most precise clocks on Earth today are optical lattice clocks, which trap atoms in grids of light and measure their vibrations with incredible accuracy. These devices are so sensitive that they can detect differences in time flow across just a few centimeters of height. Raising one clock above another by the width of a human hair produces a measurable difference due to Earth's gravity. This is direct proof that time is not universal but depends on position in a gravitational field. Even within a room, time passes differently at the ceiling than at the floor. Such effects were once unimaginable but are now daily results in modern laboratories. Time is revealed not as a steady rhythm but as a landscape with gradients and slopes. These clocks are revolutionizing more than physics. They can map Earth's gravitational field in detail, revealing underground structures or shifts in groundwater. They are tools of geology, navigation, and geophysics, using time to explore the hidden depths of the planet. Time measurement becomes a new form of sensing. The fact that clocks can disagree over centimeters shows how malleable time truly is. If these differences can be detected in a lab, imagine what happens near neutron stars or black holes, where gravity is millions of times stronger. Optical lattice clocks remind us that we already live in a world where time travel effects are measurable, even if only in tiny increments. 57. Earth tides subtly speed and slow the planet day by day. The gravitational pull of the moon and the sun stretches Earth, creating tides not only in the oceans but in the planet itself. These deformations slightly alter the rotation rate of the planet, which in turn changes the length of a day. Time on Earth is therefore not constant, it is influenced by celestial mechanics on daily and seasonal scales. Over centuries, these tidal effects accumulate. Ancient records show that days were shorter millions of years ago, and the length of a day continues to increase slowly as Earth's rotation decelerates. Our experience of time is therefore not fixed but evolving, sculpted by gravitational interactions with our cosmic neighbours. This reveals that even planetary motion acts as a kind of time machine. Dinosaurs lived under days that were shorter than ours, and future beings will live under days longer than we can imagine. Time itself is shaped by celestial relationships, not by immutable rules. When we think about time travel, we often imagine machines or wormholes. But Earth itself is already participating in slow time drift. Our days lengthen, our clocks adjust, and our calendars shift to match the evolving rhythms of the cosmos. Even without advanced technology, time is being stretched beneath our feet. 58 gravitational waves stretch time as they pass through Earth. Gravitational waves are ripples in space-time created by massive cosmic events like black hole mergers. As they pass through Earth, they stretch and compress space itself by tiny amounts. This includes time, since space and time are inseparable. For a fraction of a second, the ticking of every clock on Earth is altered ever so slightly as the wave rolls past. These changes are incredibly small, fractions of the width of a proton, but they can be measured with detectors like LIGO and Virgo. The ability to sense these waves proves that space-time is not rigid but elastic, vibrating with the echoes of distant events. Time is not immune to these distortions, it is part of the fabric being shaken. The fact that we can detect such minute shifts means we are beginning to read the universe in a new way. Gravitational waves carry information from billions of years ago, from collisions we could never otherwise observe. They are messages from the past, encoded in distortions of time itself. The implication is profound. Every passing wave is a tiny ripple in the river of time that we experience. We live not in a fixed timeline, but in a fabric that quivers with the memory of cosmic violence. Time travel may one day involve riding these waves, surfing distortions that connect distant eras. 59 strong lens systems act as cosmic stopwatches across billions of years. When light from a distant quasar is bent around a massive galaxy, it can take multiple paths to Earth. Each path has a slightly different travel time, so the quasar appears in multiple images that flicker with delays. By measuring those delays, astronomers can calculate cosmic distances and even estimate the expansion rate of the universe. Time delays become cosmic stopwatches, measuring events billions of years old. This technique turns time into a ruler stretching across the cosmos. Instead of simply seeing distant light, we can read the timing of its journey. Variations in brightness arrive at different moments, allowing us to reconstruct both the mass distribution of the lensing galaxy and the structure of the universe. Time becomes an observable quantity woven into the very shape of space. The delays are not trivial, they can span days or weeks. This means we can watch the same cosmic event replayed at different times from different angles. It is like a natural time machine that re-delivers history from multiple perspectives. The universe itself provides the reruns. These cosmic stopwatches remind us that time is not abstract but measurable across unimaginable distances. By reading light delays, we can weigh galaxies, test cosmological models, and peek into the early history of the universe. Time becomes the ultimate cosmic surveyor, carving maps of reality itself. 60, shifting alpha fine structure would rewrite cosmic timekeeping. The fine structure constant alpha is a number that governs the strength of electromagnetic interactions. If this constant were different in the past, then the behavior of atoms and light would also have been different, altering the way we measure time across the cosmos. Some studies have even suggested hints that alpha might vary slightly over cosmic history, though evidence remains inconclusive. If alpha changes, then our entire cosmic clockwork would be rewritten. Light from distant galaxies would carry a different signature than expected, and our models of cosmic expansion would need adjustment. This would mean that the way we reconstruct time from astronomical observations is not as stable as we think. Our measurements of the age of the universe would shift. The possibility raises unsettling questions. If physical constants evolve, then time itself may not be constant but fluid. What we call billions of years may be relative to the rules of physics that applied in those eras. The clock of the cosmos may not be universal but context-dependent. For time travel, this suggests that moving across eras may also mean moving across different rules of reality. A traveller to the distant past might encounter a universe where atoms behave differently and clocks ticked at other rates. Time would not just change direction, it would change character, leaving explorers in a cosmos both familiar and alien. 61. Time perception in dreams separates brain time from physical time. When we dream, our sense of time often breaks away from the rhythm of the clock. Hours can seem to pass in seconds, or entire narratives can unfold in the blink of an eye. This reveals that the brain maintains its own form of time, one that does not always align with the physical flow outside. Dreams are the clearest demonstration that mental time can split from physical time, creating personal timelines untethered to the external world. Neuroscience suggests that during rapid eye movement REM sleep, neural activity intensifies in ways that resemble wakefulness. Memories and fragments of experience are stitched together, often without logical continuity. The brain compresses or stretches time, creating the illusion of long events in short spans. While the body remains in the present, consciousness is transported into subjective durations that obey their own rules. This shows that the flow of time is not absolute, even in our daily lives. It is partly a construction of the brain, shaped by perception, memory, and imagination. In waking life, our brains synchronize well with clocks. In dreams, that synchronization dissolves, and the mind wanders through its own non-linear chronology. For the dreamer, it feels real, even though it diverges from objective time. Dream time suggests a parallel form of time travel available to everyone. While we cannot yet move our bodies into the past or future, our minds regularly escape into realms where time obeys different rules. Each night, the brain reminds us that the experience of time can be fluid, shifting between rapid compression and endless expansion. 62. Memory consolidation reorders the past during sleep. During sleep, especially deep slow-wave sleep, the brain replays and reorganizes memories. Events from the day are sifted, strengthened or discarded, creating a more coherent long-term record. This process means that our memory of the past is not fixed, but rewritten every night. Sleep alters history, not objective history, but our personal history of experience. Research shows that neurons fire in the same patterns during sleep that they did during waking experiences, as though the brain is rehearsing the past. But in this rehearsal, details can shift. Some memories are sharpened, while others are blurred or distorted. The brain is not a recorder, but a sculptor, shaping the past to serve the needs of the future. This reveals that memory is not stable, but dynamic. Each night we undergo a form of time travel, revisiting past events and altering how they will be remembered. The next day, what we recall is not the raw experience, but a modified version of it. In this sense, the past is fluid, reconstructed continually rather than preserved. The lesson is that time travel does not always involve physics. It can also be psychological. The mind itself edits history, building the past anew as we sleep. What we carry forward is not a record of what happened, but a transformed story, shaped by the hidden hand of memory consolidation. 63. Predictive coding in the brain simulates near futures constantly. Our brains are not passive receivers of information. They are prediction engines, constantly forecasting what will happen next. This is known as predictive coding. The brain generates models of the immediate future and compares them against incoming sensory data. This means we are always living slightly ahead of the present, anticipating events before they occur. This system makes perception faster and more efficient. Instead of waiting for the world to unfold, the brain guesses and corrects itself as needed. For example, when you catch a ball, your brain is already predicting its trajectory before your eyes finish tracking it. You are acting in a simulated near future created by your own mind. In effect, predictive coding makes each of us a micro-time traveler. Our consciousness is tilted forward, leaning into what is about to happen rather than resting entirely in what is. The flow of time we experience is thus shaped by constant forecasts that give us a head start on reality. If time travel is defined as accessing other moments than the present, then predictive coding is a form of continuous, everyday time travel. It does not reach into the deep past or distant future, but it lets us live milliseconds or seconds ahead of the physical now. In its own way, it shows that the mind bends time just as physics does. 64. Jet lag is proof that circadian time fights clock time. When we travel across time zones, our biological clocks clash with the external clocks of the new location. This mismatch is jet lag. The body insists it is day when it is night, or night when it is day. The result is fatigue, confusion, and disrupted rhythms. This shows that there is not one time, but multiple overlapping times: the social clock, the environmental clock, and the biological clock. Circadian rhythms are governed by cycles of hormones, body temperature, and neural activity that evolved under the stable cycles of sunlight and darkness. They resist abrupt changes, so when external conditions shift suddenly, the body struggles to adapt. In this battle, physical time measured by clocks diverges from biological time lived by cells. The tension illustrates how relative time is. For a traveller, two different nows exist: the clock time of the new place and the body time of the old. Adjusting requires days of gradual resynchronization, as biology slowly bends to the new external frame. This is a form of biological time travel, where the body carries its old time into a new world before catching up. The phenomenon reminds us that time is not only cosmic and physical, but personal and embodied. We each carry an internal time machine that can drift, lag, or misalign. Jet lag is proof that time is layered, and that living beings inhabit it differently depending on where they have been. 65. Cryonics era bets that tomorrow can fix yesterday. Cryonics is the practice of freezing human bodies or brains at extremely low temperatures with the hope that future technology can revive them. It is based on a bold gamble. The death today is only temporary if tomorrow brings cures and methods we cannot yet imagine. In essence, cryonics treats the future as a time machine that can reach back and rescue the past. The logic is straightforward. If biological processes can be paused without irreparable damage, then future science might repair what today's medicine cannot. Revival would mean awakening centuries later, stepping directly into a future you never lived through. It is not travel in the active sense, but suspension until rescue. Skeptics argue that freezing causes too much damage and that revival is unrealistic. Supporters counter that no physical law forbids it, and future nanotechnology could repair even microscopic damage. The debate remains unresolved, but the concept itself forces us to think of the future as a resource. Instead of accepting the finality of death, cryonics bets on tomorrow. If successful, cryonics would create a profound form of time travel, individuals from our century walking among societies centuries ahead. They would not have travelled across time consciously, but their lives would bridge eras nonetheless. It is a vision where the future does not just arrive, it reaches back to retrieve the lost. 66. Relativistic starships would make deep futures the reachable destination. If humanity ever builds starships capable of reaching near light speed, the consequences will go beyond space exploration. Such voyages would carry passengers into the far future of Earth. Time dilation ensures that while only years pass for those aboard, centuries or millennia would unfold for those left behind. The destination would be not just distant stars, but distant eras. The physics of this is clear. As velocity approaches light speed, the factor of time dilation grows dramatically. At 99.9% of light speed, time passes about 1/7 as fast for the traveller as for those at rest. Push closer to the limit and entire civilizations could rise and fall, while the crew experiences only a fraction of that span. This makes relativistic travel the most practical form of time travel humanity could ever achieve. It requires no exotic matter, no paradoxes, only propulsion beyond our current limits. Every starship becomes a bridge into the future, its passengers returning to Earth as witnesses of history yet to happen. The cost is isolation. Travellers would leave behind everyone they know, and by the time they return, those people would be long gone. It is time travel by loneliness, offering a glimpse of tomorrow at the price of today. Yet for explorers hungry for discovery, the lure of seeing Earth's future might outweigh the pain of leaving its present. 67. A close orbit near a black hole gives a fast jump into far futures. Orbiting a black hole at safe distance offers another form of natural time travel. Because gravity slows time, a traveller circling just outside the horizon would age more slowly than the universe beyond. After only a few years of orbit, they could return to find centuries had passed elsewhere. The black hole becomes not just a trap of matter, but a gateway to the future. This effect is not hypothetical. It is a direct consequence of general relativity. Gravity dilates time, and near a massive object like a black hole, that dilation becomes extreme. The closer the orbit, the slower time passes. For distant observers, the traveller seems frozen. For the traveller, time flows normally. The difference accumulates into a leap forward in history. Such an orbit would be dangerous. Radiation, tidal forces, and instability make black hole environments hazardous. Yet in theory, the orbit could be sustained, giving a practical if perilous way to reach future eras without needing high-speed travel. The black hole does the work for you, bending time as part of its very nature. The thought raises haunting scenarios. Could advanced civilizations place stations around black holes to skip across millennia? Could they use these cosmic giants as both energy sources and time machines? Black holes may not only end stars, they may also carry travelers into futures beyond the reach of ordinary spaceflight. 68. Tidal forces near horizons can age one part of a body faster than another. Near a strong gravitational gradient, different parts of a body experience different flows of time. If your head is closer to a black hole than your feet, the difference in gravity could cause your head to age faster than your feet. Normally, these differences are tiny and imperceptible, but near horizons they could become dramatic. The body itself becomes a divided clock. This phenomenon illustrates how local and relative time truly is. Even within a single object, different positions can experience different durations. The closer the object is to extreme gravity, the sharper the differences. In principle, the body could stretch not only spatially but temporally, with each part living a slightly different story. For a traveller, this would be disorienting. Which version of yourself is the real one? The head that has aged more, or the feet that have aged less? Such distortions force us to reconsider identity when time is fractured across the body itself. It reveals how fragile continuity is in extreme environments. Tidal time differences remind us that time travel is not only cosmic, but personal and dimensional. If every part of the body can drift into its own rhythm under gravity, then time is far less uniform than we think. Horizons and black holes expose this hidden truth. We are stitched together by time, but the stitching can unravel. 69. A future light cone limits what any event can ever influence. In relativity, the future of any event is defined by its light cone, the region of spacetime that can be reached by signals moving at or below the speed of light. This cone sets a limit on what the event can affect. Everything outside the cone is forever unreachable. Time travel to the future is therefore always constrained by this geometric structure. The concept shows that the universe has built-in boundaries to influence. Even if you live forever, you can never interact with regions beyond your future light cone. Those parts of space-time exist, but they are causally sealed away. In this sense, the future is both open and limited, shaped by the cone you occupy. For time travel, the light cone defines the scope of possibility. No matter how advanced technology becomes, no signal or traveller can leap beyond this causal boundary. The cone is the architecture of destiny, a limit written into the geometry of space-time itself, yet light cones also reveal the richness of the universe. Each person, each event, has its own cone, overlapping with others in intricate patterns. Time travel would mean moving within and between cones, finding the places where paths intersect and where influence can occur. The geometry of cones is the geometry of time itself. 70. A past light cone locks in what any observer can ever know. Just as the future light cone defines what you can influence, the past light cone defines what can influence you. Everything you see, hear, or experience lies within your past light cone. Events outside of it, too far away or too fast, can never reach you no matter how long you wait. Your knowledge of the past is therefore limited by this geometric boundary. This means that history is not absolute, but relative to perspective. You cannot see the entire past of the universe, only the past within your cone. Other observers elsewhere have different cones, with different histories accessible to them. Together, these overlapping cones form the network of causality that defines reality. For time travel, the past light cone is a reminder of constraints. Even if you could travel backward, you would only be able to access events within your causal history. The universe beyond your cone is forever closed to you. Time is not just about when, it is also about where, tied to the reach of light. The concept shows that memory itself is shaped by geometry. What you can recall and record depends on what lies within your cone. The past is not universal but local, stitched together from countless overlapping cones. To travel through time would mean navigating these stitched histories, entering the light of events that were once forever beyond you. 71. Why does relativity allow you to reach the future but not your own past? Relativity opens the door to travelling forward in time through speed and gravity. Astronauts, clocks, and particles have already demonstrated this effect on small scales, proving that the future can be reached faster than the people left behind. But the same equations make backward travel into one's own past much more problematic. Loops in time are mathematically possible in certain scenarios, but they introduce contradictions that the universe seems determined to avoid. The difference lies in entropy and causality. Moving forward aligns with entropy's increase, the arrow of time that pushes history toward disorder. Moving backwards would require reversing entropy, an act forbidden by thermodynamics on any large scale. Physics therefore grants us passage forward as a natural consequence of relativity, but it resists our attempts to bend back into earlier pages of the story. This asymmetry is profound. It means the future is always accessible through speed and gravity, while the past is sealed like a locked vault. The openness of one direction and the closure of the other hint that time may not be a symmetrical dimension despite its appearance in equations. The difference between forward and backward may be the deepest law in the universe. For time travel dreamers, this creates both hope and frustration. The future is open and waiting, reachable through physics we already understand, but our origins remain locked away, glimpsed only through light and memory. Relativity gives us a one-way ticket into tomorrow, but never yesterday. 72. What if closed time-like curves exist only in unreachable cosmic regions? Certain solutions to Einstein's equations predict closed time-like curves, paths where time folds back and loops onto itself. But instead of appearing everywhere, these structures may exist only in extreme, unreachable places. Rotating universes, cosmic strings, and Kerr black holes all permit them mathematically, but accessing them may require conditions so dangerous that no traveller could survive. If this is true, time loops are not forbidden but quarantined. They exist within the laws of physics, but in regions beyond practical exploration. Nature might allow them in principle, yet also hide them in places where no observer can exploit them. This interpretation solves the paradox problem by keeping loops outside the reach of any civilization. It also reframes our understanding of possibility. Instead of asking whether time loops exist, we might ask whether they are accessible. If they remain forever locked inside horizons or cosmic conditions we cannot cross, then they are curiosities rather than opportunities. They enrich our theories but deny us their power. For time travel, this means that backward journeys may exist only on paper. They haunt the equations but remain sealed in places no one can touch. Closed time-like curves may be real but untouchable, a reminder that the universe contains possibilities it never intends to share. 73. Is time quantized, with the smallest unit being the Planck time? The Planck time, about 10 to the negative 43rd seconds, is the smallest unit of time that makes sense within current physics. Below this scale, our equations of relativity and quantum mechanics break down, and time itself may lose meaning. If time is quantized, then reality does not flow smoothly, but ticks in tiny increments, like frames of a film. If true, this would mean that continuous time is an illusion. Our perception of smooth flow would be a trick, much like a movie looks continuous even though it is built from still frames. Time would consist of discrete chunks, indivisible units that set the ultimate resolution of reality. Nothing could happen between Planck ticks, because no between would exist. This changes the conversation about time travel. If time is granular, then moving backward or forward might involve skipping frames rather than sliding smoothly. Technology that could manipulate Planck-scale intervals might allow shifts across the timeline, jumping between frames the way an editor jumps between shots. The possibility of quantized time suggests that reality is fundamentally digital. Just as computers encode information in bits, the universe may encode existence in Planck-sized ticks. To travel in time may mean learning how to edit those ticks, stepping outside the projection into the machinery that drives the film of reality. Time has always been the most mysterious companion of existence, guiding us from one heartbeat to the next while hiding its deepest secrets just beyond our reach. Tonight we have travelled through its paradoxes, its cosmic horizons, its quantum whispers, and its gravitational bends. What emerges is not a final answer, but a truth far more powerful. Time is not a straight line, but a living fabric that shapes every star, every memory, and every dream. Whether we step into the future through relativity, glimpse the past through starlight, or bend reality in thought alone, we are already time travelers in ways we rarely notice. And perhaps the greatest discovery is that the journey never ends, because in exploring time, we are really exploring ourselves. If you enjoyed this journey, don't forget to like the video, comment, and subscribe to our channel. With your support, we can make this community of science and discovery even bigger. Share your ideas with us, because it's always more exciting to explore the unknown together. As Carl Sagan said, reality may be much stranger than we realize. Science is the most powerful way to understand this strangeness.